Okay, well, as you know, the number of particles in 1 mole of any substance is the same number as in 1 mole of any other substance. It's called Avogadro constant. It's 6.022140857 by 10 to the power 23. There it is, and there it is written out in full. Huge, huge number. Now, I thought you were going to say that you're impressed with the fact that I knew that to 10 significant figures. The question is that a universal constant? You mean like the speed of light or Planck's constant? No, it's not at all. What are essentially universal constants, well, I don't think we call them that, are the masses of the atoms of all the elements, at least the masses of the isotopes of all the elements. They're constant. But over the course of time, human beings, scientists are human beings, have made decisions, have made assignments of values of what are standards, and that over history has led to this being a human construct. The way that history has developed, the way that science developed over time, could have led us to any other value if we had begun with different definitions of how we define the relative masses on the atomic mass scale, of what is the standard of 1 gram of mass, and things like that. So that's just where we are at now in the course of history. Why? Excellent question. Why is it that particular number? All right, I'll give you a short history, simplified and not taking any notice of the fact that still today debates rage about how mole should be defined, all sorts of things related to stoichiometry. So just the conceptual essence of what has happened without much attention to why it happened. Early 1800s, 200 and a bit years ago, people like John Dalton began to be able to estimate the relative masses of atoms, of different elements, the weight of one compared to another. Relative, not absolute masses. When you've got a list, when you've got a pile of relative anything, heights, masses, it's natural to put them on one scale of values relative to each other. And it's common, but not necessarily. So, on a scale, it's natural to assign the one at the bottom, the lowest one, a value of 1. And that's what scientists have done with the relative masses of atoms, of the elements. So the lightest one, to which they gave a value 1 was, hydrogen. So on the scale that was first constructed, they said, hydrogen, take that to be 1. Exactly. So essentially an infinite number of decimal points. And on this scale, so we've got hydrogen, helium, lithium, beryllium, boron, each one relatively heavier. And on this scale, we go down to, or up to, say, let's take nitrogen, experimentally, about 14.0, quite close to 14. This is by assignation. This is experimentally based upon that one. And that says that an atom of nitrogen is 14.0 times the mass of an atom of hydrogen. So any mass of nitrogen atoms, which is 14 times the mass of hydrogen atoms, they'd have the same number of atoms, and that's the basis of the mole. And it made sense at the time. Gram was the common working standard of mass, so they took 1.00 grams to be 1 mole of hydrogen, 14.00 grams of nitrogen atoms to be 1 mole of nitrogen atoms, and so on for all the rest. It doesn't matter so much to our story, but later the scale of relative atomic masses was changed to a standard of oxygen. naturally occurring oxygen. And this made a slight difference to the scale, because on this scale oxygen was quite close to 16. It changed it to 16, but oxygen as it occurs naturally has 3 isotopes, mainly 16, but there's also 17 and 18. And naturally occurring oxygen from these plants in this rock, in this air, is slightly different. The distribution of these 3 in naturally occurring oxygen is a little different. So when you take an average, and this, I didn't say, this is the average of naturally occurring oxygen in nature, that's variable from place to place. Well, you can't have a standard that's variable. So the governing body of chemistry nomenclature, standards, units, and so on, are UPAC, the International Union of Pure and Applied Chemistry, made a decision to base the standard on this scale of relative masses, something which doesn't vary, and that is isotopes of carbon, isotope 12, and decided that that should be given, assigned on this scale, a relative mass of 12 exactly. And that's not variable. And that's been the definition, I believe, since 1961 or something like that. And the best estimate of the number of those atoms in 12.00 grams of it is that number. And that's how it comes to be. Now, all experimental measurements or estimates have got an uncertainty. So I've quoted this one to, I think, 10, but we know we're pretty sure about it to 9, but it still has an uncertainty. And what IUPAC is just in the process of doing is redefining 1 mole as the amount, as not the amount that is in 12 grams of carbon-12 isotopes, but as the amount that has that many particles, exactly that many particles. That's not subject to measurement. It's free of any error of uncertainty, of determination, of estimation. So that's where that comes from. So going back in time, people could have assigned a value for this isotope as, on this scale, 100, or 1, or 7,642. Historically, it's the way that this happened, starting off with that one originally, it's assigned to be 12. People in the past could have defined 1 gram as not 1,000th of this piece of gold, I think it is, in Paris, I think it is, weighing, which they decided should be taken to be 1 kilogram. They might have taken a smaller chunk. They might have taken a bigger chunk to define 1 kilogram. And those sorts of decisions would have changed what this entity is. But there would have still been a self-consistent set of values. You'd have still had to go through the same calculations that you're doing now and come up with the same answers in the end in your stoichiometric calculations. But IUPAC could decide tomorrow, they won't, but they could decide that the number of particles in 1 mole is 654 or 1.74 by 10 to the 14. But then you would need an awful lot of moles of a substance to have practical masses, practical amounts that you can weigh out, because weighing is how we count in chemistry. Human construct based upon the way that history of decision-making and assignation of values has taken us. Pardon? Aha, indeed. I've loved your questions. Let's have more of them. Every lecture. Thank you. Okay, yeah. See you tomorrow.